This video, we are going to talk about how to prove the Wallis infinity product for pi. This problem normally arises from the situation where we have I of n equals integral from 0 to pi of sine x exponent n dx. So let's first find the reduction formula. Let's rewrite this as equal to integral of 0 to pi onto sine x exponent n minus 1. But because I put n minus 1 here, I need to multiply by sine x, then dx. So from here, we can differentiate sine x exponent n minus 1 and then integrate sine x. So let's let u to be equal to sine x exponent n minus 1. So du is equal to, bring n minus 1 down. Then we'll multiply by sine x exponent. Now it becomes n minus 2. And if we differentiate sine x itself, it becomes cos x dx. Then here, let's let div to be equal to sine x dx. So if you integrate div, we will get v, which is equal to, if you integrate sine x, you get minus cos x. So we know that I of n is equal to, so using the integration by parts, that is uv. So our u is sine x exponent n minus 1. Then v is minus cos x. All of this evaluated at 0 and then pi on 2. Then minus integral from 0 to pi on 2 of v du. V is minus cos x. Then du is times into bracket n minus 1. Then sine x exponent n minus 2 cos x dx. So now, I of n is equal to, if we multiply this becomes minus cos x sine x exponent n minus 1, evaluated at 0 and pi on 2. Then at this side, we have integral from 0 to pi on 2. However, let's bring this constant out. And then here's minus. Minus times minus will make here plus. Then the constant is n minus 1. So integral of 0 to 2. Now you see that here's cos x, here's cos x. So it becomes cos squared x. And then times sine x exponent n minus 2 dx. Now, let's do this. If we put in pi on 2, cos pi on 2 is 0. And if we put in 0, sine 0 is 0. So all of this goes away. So we are only left with n minus 1 times integral 0 to pi on 2. However, this cos x is the same as into bracket 1 minus sine squared x, then times sine x exponent n minus 2, then dx. So what we'll do in this case is that we can break this integral into 2. So let's break the integral into 2. So I of n is equal to, into bracket, n minus 1. Integral of 0 to pi on 2. Then 1 times sine x exponent n minus 2 is the same as sine x exponent n minus 2 dx. Then minus into bracket n minus 1. Integral of 0 to pi on 2. Then sine x exponent n minus 2 times sine squared x will give us sine x exponent n dx. So you see that from here, I of n is equal to, into bracket n minus 1. All of this becomes I of n minus 2. Then minus into bracket n minus 1. All of this becomes I of n. So if we further simplify, we can expand this. So I of n is equal to, into bracket n minus 1, I of n minus 2. Then minus n I of n. Then minus 1 times minus 1 becomes plus 1. So plus I of n. So you see that this I of n and this I of n can cancel out. So you can bring minus n I of n to the left hand side. So it becomes n I of n is equal to, into bracket, n minus 1 I of n minus 2. So if we write the final answer, we can see that if we divide through by n, I of n is equal to n minus 1 over n. I of n minus 2. So from the question, we're given that I of n is equal to integral of 0 to pi on 2 sine x exponent n dx. And then we establish that I of n is equal to n minus 1 over n, I of n minus 2. Now, based on the reduction formula we got, you can see that we can have the case of even numbers, and then we can also have the case of odd numbers. So for even numbers, we have to look for the case of I of 2m. And then for odd numbers, we have to look for the cases of I of 2m plus 1. So let's start with the even numbers. So what is I of 2m? What it means is that wherever we see n here, we need to replace it with 2m. So this becomes equal to 2m minus 1 divided by 2m. Then I of n minus 2 becomes I of 2m minus 2. So let's find I of 2m minus 2. So I of 2m minus 2 becomes, so we replace, wherever we see m, we replace with 2m minus 2. So this becomes 2m minus 2 minus 1 divided by 2m minus 2. Then here becomes I of 2m minus 2 minus 2. So I of 2m minus 2 is equal to, here becomes 2m minus 3 divided by 2m minus 2, I of 2m minus 4. Now, let's find I of 2m minus 4. So I of 2m minus 4 is equal to, here becomes 2m minus 4 minus 1 divided by 2m minus 4. Then I of 2m minus 4 minus 4, then minus 2. So I of 2m minus 4 is equal to 2m minus 5 divided by 2m minus 4, then I of 2m minus 6. When you keep on and on, you come to the place where you get I of the smallest even number, and then the smallest even number in this case is I of 0. So now let's find I of 0 from this. So I of 0 becomes integral of 0 to pi on 2. Now sine x exponent 0 is 1 dx. So this becomes x evaluated as 0 and then pi on 2. And if you put in the limits, you get I of 0 to be equal to pi over 2. So if we write I of 2m, I of 2m is equal to, the first one was 2m minus 1 divided by 2m, I of 2m minus 2. And I of 2m minus 2 is times 2m minus 3 divided by 2m minus 2, I of 2m minus 4. And I of 2m minus 4 is, here was 2m minus 4. So I of 2m minus 4 is times 2m minus 5 divided by 2m minus 4, I of 2m minus 6. And when we keep on, we reach the point where we have to look for I of 0. So now you can see that I of 2m is equal to 2m minus 1 divided by 2m, then times 2m minus 3 divided by 2m minus 2, then times 2m minus 5 divided by 2m minus 4, then I of 0, which we found as pi on 2, so times pi on 2. So from the equation, we established that I of 2m is equal to 2m minus 1 divided by 2m times 2m minus 3 divided by 2m minus 2 times 2m minus 5 divided by 2m minus 4 times pi over 2. So let's continue. So I of 2m is equal to 2m minus 1 divided by 2m. Now I want us to multiply this by 2m divided by 2m. 2m divided by 2m is 1. So if we multiply by this part, this term is still the same term. So we've done nothing to the equation. Then here is 2m minus 3 divided by 2m minus 2. I want us to multiply that one to by 2m minus 2 divided by 2m minus 2. then times 2m minus 5 divided by 2m minus 4. I want us to multiply this part 2 by 2m minus 4 divided by 2m minus 4, then times pi over 2. So I of 2m is equal to, now let's first write 2m first. So 2m times 2m minus 1, then times 2m minus 2, then times 2m minus 3. Here's 2m minus 4, so times 2m minus 4, then times 2m minus 5. All of that divided by, here becomes 2m times 2m is 2m squared. Then 2m minus 2 times 2m minus 2 is 2m minus 2 squared. 2m minus 4 times 2m minus 4 becomes times 2m minus 4 squared. All of that times pi over 2. So I of 2m is equal to, now see, here's 2m times 2m minus 1 times 2m minus 2 times 2m minus 3 times 2m minus 4 times 2m minus 5. And all of that is 2m factorial. All of that divided by, now let's pull out 2. So if you pull out 2, it becomes 2 squared times m squared. Then times, if you pull 2 out here, it becomes 2m times m minus 1 squared. Then if you pull out 2 in this case too, it becomes 2 squared, then times m minus 2 squared, then times pi over 2. So, sorry, here's 2m. So I of 2m is equal to 2m factorial time divided by, now you can see that this 2 squared will keep repeating itself for m times, and therefore here is 2 squared exponent m. Then here's m minus 1, m minus 2, so that's m factorial. So times m factorial, but all of that is squared times pi over 2. So we are done with the case of I of 2m. Let's come to the case of I of 2m plus 1, which is the odd number case. So if you put in, remember that our reduction formula I of n is equal to n minus 1 over n, I of n minus 2. So I of 2m plus 1 becomes 2m plus 1 minus 1 divided by 2m plus 1. I of 2m plus 1 minus 2. So I of 2m plus 1 is equal to, now 2m plus 1 minus 1 is 0, so it becomes 2m divided by 2m plus 1, I of 2m minus 1. Now let's find I of 2m minus 1. So this is equal to, so 2m minus 1 divided by 2m minus 1, I of 2m minus 1 minus 2. So this is equal to, so I of 2m minus 1 is equal to I of 2m minus 2, then divided by 2m minus 1, I of 2m minus 3. So let's find the case of I of 2m minus 3. This is equal to 2m minus 3 minus 1 divided by 2m minus 3, I of 2m minus 3 minus 2. So I of 2m minus 3 is equal to 2m minus 3 minus 1 becomes 2m minus 4 divided by 2m minus 3, I of 2m minus 5. So you can see that the cases of I of 2m plus 1 is equal to, the first one is 2m divided by 2m plus 1, then times, the next one 2m minus 1 is 2m minus 2 divided by 2m minus 1, then times I of 2m minus 3, which is 2m minus 4 divided by 2m minus 3, times, now when we keep on, we'll reach the case of the least number of the least odd number, which is I of 1. So let's find I of 1. So if you put I of 1, remember that from the question, I of n is equal to integral of 0 to pi on 2 sine x exponent n dx. So I of 1 is the same as integral of 0 to pi on 2 sine x exponent 1 is the same as sine x dx. And if you integrate sine x, you get minus cos x evaluated as 0 and then pi on 2. Now minus cos pi on 2 is 0. So minus cos 0, which is 1, and therefore this will give us 1. So what it means is that I of 2m plus 1 is equal to 2m divided by 2m plus 1 times 2m minus 2 divided by 2m minus 1 times 2m minus 4 divided by 2m minus 3. I of 1 is 1, so times 1. So we get the cases of the odd numbers as I of 2m plus 1 equals to 2m divided by 2m plus 1 times 2m minus 2 divided by 2m minus 1 times 2m minus 4 divided by 2m minus 3. So let's continue. I of 2m plus 1 is equal to 2m divided by 2m plus 1. Let's multiply both the numerator and denominator by 2m divided by 2m. Then times 2m minus 2 divided by 2m minus 1 times, here becomes 2m minus 2 divided by 2m minus 2. Then times 2m minus 4 divided by 2m minus 3. Now let's multiply numerator and denominator by 2m minus 4 divided by 2m minus 4. So I of 2m plus 1 is equal to, the numerator becomes 2m squared, then times 2m minus 2 squared, then times 2m minus 4 squared, divided by, now the denominator is 2m plus 1 times 2m, then times 2m minus 1 times 2m minus 2, then times 2m minus 3, then times 2m minus 4. So I of 2m plus 1 is equal to, if you keep on, now let's factorize 2 out. So if you pull 2 out, it becomes 2 squared, then times m squared, then times, if you pull 2 out here, it becomes 2 squared times m minus 1 squared. And if you pull 2 out here, it becomes 2 squared times m minus 2 squared divided by, now here is 2m plus 1. If you subtract 1, 2m, subtract 1, 2m minus 2, and then subtract 1 again, 2m, sorry, here is 2m minus 1. So if you subtract m from 1 from 2m, you get 2m minus 1. Subtract 1, 2m minus 2. Subtract 1, 2m minus 3, and subtract 1, 2m minus 4. So this is 2m plus 1 factorial. So I of 2m plus 1 is equal to, now these 2 squares will keep repeating itself m times. So it will become 2 squared exponent m. And then m times m minus 1 times m minus 2. That's the same as m factorial all squared divided by 2m plus 1 factorial. So remember that the case of the even numbers was I of 2m is equal to 2m factorial times 2 squared exponent m times m factorial squared times pi on 2. So now what we can do is that let's find I of 2m divided by I of 2m plus 1. So this is equal to, I of 2m is 2m factorial divided by 2 exponent 2m times m factorial squared, then times pi on 2. Then now, because we are dividing over 2m plus 1, if we divide this, we can multiply by inverting it. So this 2m plus 1 comes to the numerator factorial divided by 2 exponent 2m, then times m factorial squared. So if we do this multiplication, you see that I of 2m divided by I of 2m plus 1 is equal to, now here is 2m factorial times 2m plus 1 factorial. So 2m factorial times 2m plus 1 factorial divided by, now look at this 2 exponent 2m, then here's 2 exponent 2m. So that becomes 2 exponent 4m. Then here's m factorial times m factorial. So we get m factorial exponent 4. Then times pi over 2. Now let's make pi over 2 the subject. If we make pi over 2 the subject, we find out that we need to invert this and multiply by I of 2m divided by I of 2m plus 1. So this is equal to 2 exponent 4m, then times m factorial all exponent 4 divided by 2m factorial, then times 2m plus 1 factorial, then I of 2m divided by I of 2m plus 1. So we got pi over 2 as equal to 2 exponent 4m times m factorial exponent 4 divided by 2m factorial times 2m plus 1 factorial, then times I of 2m divided by I of 2m plus 1. Now, remember that we said I of n is equal to integral 0 to pi on 2 sine x exponent n. So what it means is that, remember that the value of sine is between, in this case, since the limit is between 0 and pi on 2, the value of sine is between 0 and then 1. So since the value of sine is between 0 and 1, for higher powers of n, I of n begins to decrease. So what it means is that I of 2m plus 1 is less than or equal to I of 2m, which is also less than or equal to I of 2m minus 1. Now, let's divide through. If we divide through by I of 2m plus 1, then here becomes 1 less than or equal to I of 2m divided by I of 2m plus 1, which is less than or equal to I of 2m minus 1 divided by I of 2m plus 1. So now, 1 is less than or equal to I of 2m divided by I of 2m plus 1, less than or equal to, this is the same as 2m minus 1 divided by 2m plus 1. Now, let's take limit. So limit as m approaches infinity of 1 is less than or equal to limit as m approaches infinity of I of 2m divided by I of 2m plus 1, which is less than or equal to limit as m approaches infinity of 2m minus 1 divided by 2m plus 1. Now, in this case, we need to use L'Hopital's rule. If you differentiate 2m minus 1, you are going to get 1. Then if you differentiate 2m plus 1, you are going to get 1. So this becomes limit as m approaches infinity less than or equal to limit of 1 less than or equal to limit as m approaches infinity of I of 2m divided by I of 2m plus 1 less than or equal to limit as m approaches infinity of 1. So you can see that this limit is 1 less than or equal to limit as m approaches infinity of I of 2m divided by I of 2m plus 1, then which is less than or equal to limit as m approaches infinity of 1 is 1. So what it means is that now, using squeeze theorem, we can conclude that limit of as m approaches infinity of I of 2m divided by I of 2m plus 1 is equal to 1 using squeeze theorem in this case. So now what it means is that all of this I of 2m divided by I of 2m plus 1, if we take limits, this will go to 1. So it means that pi over 2 is equal to limit as m approaches infinity of 2 exponent 4m times m factorial all exponent 4 divided by 2m factorial times 2m plus 1 factorial. So this is the Wallis expansion for pi.